Okay, so there are two issues there yesterday. One of them I forgot to think about, so I can't think about it in the evening. So I still don't have an answer, but I will think about it in the future. The other issue is this. You asked me about the infimum.
Yes.
If I have a function such that the infimum over all numbers of this supermum of a supermum over x of fx minus c, right? So actually there was an error there. What I should have done, if you remember what we did, we bounded this by something like there was fxtx minus the constant, the constant c we bounded by this thing.
Mm-hmm.
So what we don't, it's not really an infimum over all numbers. I mean, you could do it, but it's much easier this way. Do the infimum over all
numbers of the
y in G. Okay, so all I need are numbers that come up from the range of f, from the image of f. So I can put here fy. Okay, fy, right? And then this I managed to bound by something like this, right? And and then if I bound this and I show that it's 0, okay, so what does this mean?
Or they want to go from something that is uncountable to something that is countable?
It doesn't have, it's not necessarily countable, but it's just that I can do this, that I can fix a specific number and not, okay, in fact, I don't really need to do this, but I wanted you to know that, okay, let's suppose it succeeds. Okay, so what does this mean? What does this mean? This means, so the conclusion was that this is 0. And you wanted to ask, why does this tell me that the function is constant? Okay, so
if and only.
Well, if it's constant, then obviously it's true. Okay, so if this is true, why is it constant? Well, this tells me that for every epsilon, there exists some xi epsilon, okay, such that for every x in G, f of x minus xi is at most epsilon over 2. Okay, I hope I'm doing something correct because I thought of it on the train on the way here. So, right? So f.
Yes, supermum is yes.
Xi depends on epsilon, right? I mean, supermum, the infimum is 0, meaning for every epsilon I get the infimum below epsilon over 2. The infimum is below epsilon over 2, the supermum here, so this means for every. Okay? But what does this mean? This means that for every x and y in G, f of x minus f of y is less than or equal to epsilon over 2. To epsilon. By the triangle inequality. But then I have for every epsilon exists xi, which I don't care about, right? I lost xi. Yeah, we lost it. So this means that it's constant. Okay? So this is basically saying that you cannot get the distance to the set of constant functions.
Be 0 without
it cannot be 0 without being.
Let's say the other way around, that if the function has at least 2 different values, then you can't get closer to both of them than the distance between half of the distance between them.
Yeah.
It can't be too close to both of them.
If you have a function with no constant, you find 2 different values, right? So you take the xi, so you take
the difference.
The difference is bigger than half of
the half of it, and that's
so this is like saying that if you take the constant function, this is closed, right? And one function is compact. The distance between a compact set and a closed set cannot be 0 unless they intersect. The function has
I have to be careful on what topology we're talking about. But probably there is a compactness in the background. But you know, it's just a simple. Maybe the runs is always simpler. Yeah. Yesterday somebody said we were being recorded. But I need to talk to the so we'll have to talk to you about something. Apparently my agendas are not good. I always get advice from you. I won't say who said. So the next thing I want to do, let me.
Are we going to do again again we didn't finish the.
Yeah. So at the end of so the second issue, okay, there's one more issue with the B. I didn't have time to think about it. I was doing things late last night. I have to make a presentation. It was terrible. For next week. So I was busy, and then it was too late for me to think about things. But so I apologize. I will give you an answer on the B thing. But there was another.
You can put it in the exercise sheet and then we.
Yeah, I know. I'm aware of
No,
these
because
things.
if it's such an obvious, we can maybe think about it ourselves.
Yeah, maybe. Well, if you come with an answer, then maybe
Yeah.
okay. Maybe I give you bonus
Okay. Now we're talking.
chocolate or something.
I suggest putting Nadav in charge of the exercise.
By the way, if you find any improvements on anything I'm saying or mistakes or something, then please tell me. I mean, this part of this being in a graduate course is participating as much as you can in the course. I could have let you read and lecture, right? And I could have done it that way. Yeah. So we said proposition F is mu harmonic, right? F is mu harmonic if and only if fxt is a martingale, where xt is the corresponding random walk, right? This is what we said yesterday. In fact, this is not just for mu, just for groups. This is true for any irreducible Markov chain. Harmonic function with respect to the Markov chain would just mean that Pf is F, right? And of course, things converge absolutely. Okay. So I could maybe do P harmonic if and only if an X where, so here xt. So P is an irreducible stochastic matrix. Then F is harmonic if and only if this. So xt is the Markov chain. Okay, so on some state space. Okay, and for the proof, I started getting messed up. Very easy. Okay, I want to remind you, what is PF at the point X? What is PF at the point X? This is exactly the expectation, right? Started at X of fx1, right? Just average the values starting at X. Another way to say this would be, this is the expectation. So this is Markov property, right? The expectation of fxt plus 1 conditioned on xt is equal to X. Same thing, right? If I can condition on this event, right? It's the same thing because of the Markov property. Markov property is if you condition on X equal to X, then this thing just behaves like a Markov chain, one step of a Markov chain. Okay. Now, I mean, of course, so this is equal to Pfx. Okay. So all you need is the ability to get to X, which comes from the irreducibility. Okay. And also, if you ask about integrability, well, integrability is just P of the absolute value of F, and you can see that it also going both ways. And from here, it's very easy. So one direction. So if F is harmonic, right? So this direction, if we assume that F is harmonic, then PF is equal to F, right? Then PF is equal to F. So, right, harmonic means PF is equal to F, or Laplacian F is equal to 0, right? The same thing, okay? And so the expectation, what do we need to show? We need to show this is a martingale, so we need to understand what this means. Where Ft is the natural filtration, right?
But does it matter? You can show this is harmonic with respect to this, right? Yeah. Or this is not filtration. Oh.
I started with a harmonic function, and I want to show that it's martingale. Okay, so from formally, I need to prove this. The fact that this is integrable comes from the fact that it was a harmonic function. That's just okay. I'm not going into those issues, but then I need to show that it satisfies that it equals ffx.
What did you write over the equal?
Markov. This is the Markov property. Yeah. Markov property tells you if you
Yeah.
condition on being at x, it's like starting at x. So it's
Mm.
these two things right.
Yeah.
This does not have anything to do with harmonic functions. This is just for any function, as long as everything converges. Right? Okay.
Let's say so you have a random walk, you apply an harmonic function to that, you get a random walk.
No. Applying a harmonic function, you're throwing everything into the real numbers or the complex numbers or something. We're thinking of real valued functions. I said just the real part and imaginary part.
So the Markov property is of what? Of xt,
Of,
right?
of x.
The thing that you
The
can
Markov
drag
property of
over
X.
T, there wasn't any
The
T.
distribution of this guy, right, looks like the distribution of f of x1 in the
Mhm.
measure ex.
Okay.
That's the Markov property, right? The distribution of this guy looks like a Markov chain in one step started at x. If you apply an f to that, you get f of a Markov chain started at x.
Right.
Okay. I mean, that's just
Mhm.
so. Expected value of this with conditional expectation of this. But what is it? By what I wrote there, right? This is exactly equal to. Okay, so
We know the formula.
we know what xt is, right? We know what xt is. Okay, let's write it this way. Sum over all x, okay, expectation of f of xt plus 1, say indicator that xt is equal to x. Condition on ft, right? This I can do, okay? And this thing is measurable with respect to ft. So it comes out.
We know the
But
formula.
before I pull it out, I know that if xt is equal to x, this thing I want to say that this is P.
We know the formula, right? And the
What? No, sorry. Yeah, okay. Sorry. Wait, what do I want to do now? I'm confused again. Okay. The conditional expectation of this thing, what is it? You're just taking expectation with all the knowledge you have. You have the knowledge of where xt is, so you have to average the next step. Okay? You have to average the next step. Okay, so what this would be is it would be sum over y, right? Conditional probability that xt plus 1 is y conditioned on ft, right? I can do it this way, right? This is how you compute expectations. So average the possibilities and multiply by the value. The value would be fy in this case. Okay, that's what I want. And now the conditional probability that xt plus 1 is equal to y conditioned on everything in the past, this is the Markov property. It tells me that it's just, right?
it's another sum.
This number, this is a random number, right? It depends on xt, and it's just a probability to go from xt to a specific y. Okay, so you see that this sum becomes just pf xt. This is what I want. Pf xt is this conditional expectation. If you know what happened up to time t, then what is your expectation? It's just p of where you were now, where you are at time t, right? So it's a random, this is a random equality. Okay, it's an almost sure equality. Okay?
This is like the formula for expectation only for conditional expectation.
Yeah, I mean, we said that conditional expectation you can average, just compute expectation where you think of this being constant.
As a random.
Yeah. So, okay, you can check. Another way to do it, go over all the possibilities of xt, right? I mean, this thing, you can, there's a partition of the space of the values of xt, and then when you know xt, you know how to get the expected value of.
If we wanted to write it like more explicitly, we would run over all the options of xt and we divide by the probability.
Yeah. Okay. Yeah.
Is that lower bracket
because it's a Markov.
Yeah, this is the Markov property.
Okay.
This is exactly the Markov property. The conditional probability of xt plus 1 equals y conditional on ft is exactly the probability to jump from xt to y. Okay. Now, I didn't use the function as harmonic. I just showed you this equality. This is just rewriting things. Okay. Just this is still true for every f, right? But you see that if f is harmonic, this would imply that the conditional expectation of f of xt plus 1 is f of xt, right? So, so this shows you that it's a Martin. Okay. Okay. Now another thing would be to show the other direction. The other direction would be that I assume that I have a martingale and I want to prove that PF is equal to F. So I fix X. I find some T such that I can get to X at time T, just so that I can condition on this event. And then I look at this, I look at what PF of X is. I already told you it's exactly the expectation F of xt plus 1 conditioned on xt equals X. Right? Okay, what is this? This is the same as writing the expectation, indicator xt equals X, divided by the probability that xt equals X. This is the same thing. Now do conditional expectation, right? Now do conditional expectation. Do conditional expectation here with respect to ft. This guy is measurable. This guy, you get the next step of the random, right? So what did I get here? Yeah, so I do the expectation of conditional expectation of f xt plus 1. I need to use the fact that I'm a martingale times the indicator xt equals X. Why is this true? I did conditional expectation of conditional expectation and pull the indicator out because it's measurable. Okay, and then I have to divide everything by the probability that xt is equal to X. And now what is this guy? We assume that f of xt is a martingale, so this guy is just f of xt. On this event, it's just f of x. Okay. So the f of x comes out, and you get the expectation of the indicator divided by the probability, which is 1. So you just get f of x. Okay. So if you start from a martingale, I use the martingale here. Start from a martingale, you get a harmonic function. Okay. So this is the reason. This is the reason why harmonic functions are inherently probabilistic objects, because they have to do with martingales. Okay? You could look at it from a dynamical point of view, and you have all these things that can talk to Yair. But you could look at it from a probabilistic point of view, because these are inherently probabilistic objects. They come from. They have to do with martingales. So that's what I wanted to say. Now I want to move on to the next thing I wanted to talk about was finite index subgroups. Okay. So first of all, notation that I will keep. If I have a Markov chain, I'm going to write this for subsets and elements. Okay, I want to say what T plus for sets and elements. So these guys are just going to be T of the singletons. So I just save up on brackets. Okay, that's easy, but I need to tell you what T and T plus of A. This is just the first hitting time of where xt is the Markov chain, okay? And this will not be the first hitting time of A, we saw sometimes it's interesting to look at the first return time to A. Okay? Why do I call it the return time? If you start in A, it doesn't count the first visit. Okay? It doesn't stop immediately. It waits till the second time you're in A. Of course, if you start outside of A, these two things will be the same thing, right? So it depends on the starting distribution or the starting position. Okay? So this will be the first time after 1 that you're in. Okay. This will be standard notation for the rest of the course. I always use this notation. Okay? You have to sometimes be careful. These things might be different here and there. So first of all, I want to show you lemma. Suppose that H is a finite index subgroup inside G.
So Ariel, if you started inside a set and you took one step and you are still inside that set, so your return time
Is 1. You started in the set,
so it doesn't matter.
and you
if
took one step and you're still in the
Yeah.
set, then T is 0 and T plus is 1. Okay? You started outside the set and you took one step and you're in the set, and they're both 1. If you started outside the set and you took 15 steps and then you're in the set, then they're both 15. So GH, so H is a finite index subgroup of G. I did not say normal subgroup, just any finite index subgroup. Okay. Then, and suppose that mu is a nice measure on G. I don't always need all the assumptions, but we can put them in. Okay. My claim is that there exists some delta such that the and some constant k such that the probability, should use C maybe C. The probability that T, probability starting from yeah, so that's why it's not just the identity. So for any x in G, probability that I start from x, the T plus H, the first return time to H, okay, to the subgroup, is bigger than T, this decays exponentially. With some maybe little delta, and I put a C here. You can always get rid of the C, because this, this could, when you take T to 0, this is just 1, right? T is discrete. So you could always swallow the C into the delta somehow. But that's right.
That all depends on G, H, and mu.
On everything. Proof. Well, it has exponential tails. Specifically, has finite expectation. Everything's right. It's almost surely finite. I'm using a finite index. This is not true. It's definitely not true if you have an infinite index, even if you have the simplest, dumbest infinite index. It's completely not true. In fact, if H would be of infinite index, then TH would have infinite expectation. You see there's a really, really sharp transition between having finite index. Jump from a random variable which has exponential tails to a random variable which has infinite expectation. In fact, of course, in some situations, it will even be infinite with positive probability. So, so the proof is as follows. Consider so we are going to use the group structure here. This is, we have index, we have this, right? So consider the mu random walk xt, okay? Right, so what does this mean? This is multiplication of independent new elements, right? And then consider the process hxt. What is this process? Where does it live? This lives in the coset space of H, right? In the cosets of H. It takes values in the cosets of H. Right. Well, sorry. Okay. I claim though this is a Markov chain. I don't care which coset you're in. This is not a non-trivial statement because I'm looking at, suppose I tell you you're in some coset. What is the probability that you jump to another coset? It only depends on the coset. It doesn't depend on the specific element in the coset. Okay? So you somehow have to get, so exercise this is a Markov chain. You have to prove that this is a Markov chain. What do you need to prove? You need to prove that the transition probabilities don't depend on the cosets. Okay? Okay, so it's not very hard. It's good basic. Once this is a Markov chain, and this is because the group track, you can think of it the following. You have a computer, right, that knows how to sample these things, right? So one way to sample, just sample independent mu elements and multiply them, right? But how can you do the cosets? Same thing. You give me which coset you're in, I tell you, okay, just take any representative and multiply that by the new element. This will move you to the proper coset. And all I needed, I didn't really care where I was in the coset. It would always move to the same coset. I basically gave you the proof, but I mean, heuristically, this has to be the case. Okay. So this is a Markov chain. Now, you can also check. I mean, this is very easy. That since U is adapted, what does this mean? It means I can reach every point in G. Then I can reach every coset in G. Why? You want to reach a certain coset, take some representative, reach that representative. Of course, if you're in a representative, you're in the coset. Okay? So since we use adapted, hxt is irreducible. Now, I do not want you to confuse. This is a Markov chain on some abstract state space, finite, okay, of a certain size. This is not a random walk on a group. It is a random walk on a group if H is a normal subgroup, but it's not a random walk on a group. You cannot look at it as a random walk on a group if H is not a normal subgroup. Okay, Nadav said Schreier graph, but yeah. Okay, Schreier graphs are not Cayley graphs. Okay, in fact, it's not really a walk on a Schreier graph. You could assume that you have, arbitrary transition. It's a weighted Schreier graph. Okay, so it is a network. It is a network. Will be a network. So, finite network. So when I say here irreducible, I mean irreducible is a Markov chain. You can reach any coset, right? Now we have an irreducible Markov chain, and we know that for any x in G, right? Or let's write it this way: for any hx, okay, or any coset. How do I write this? Am I supposed to write it this way? No. What is the other way?
This is weird.
No, it was fine. No.
Which way do I write? For
Right.
me, the H is on
The
the
H
left
is on
or
the
left.
left,
Yeah.
yeah.
Okay. So this tells me where the
The
H
H
goes.
is on the left.
Yeah, I always write them on the. I always write this for both left and right cosets, and then let you understand from the context which it is. But I know that there are strong feelings in our department about this.
And then people start writing G over one side.
Yeah. When you do things like that, this I never do. This I never do. This I never
Who
have.
does that?
Who does it? More important people than me. Luckily, most of them now went to America. So, okay. So for all so for any coset, that's all I need. For any coset specifically, fix a coset. You don't care about who the exact representative is. You'll see the probability under this Markov chain. So I can write hx, right? The probability that I start from this position. So for any coset, there exists some say t, which depends on this coset. So t is t of hx. Okay, depends on the specific coset. Okay, such that the probability hx, right, such that xt, not xt, but rather hxt, right, the Markov chain that I'm looking at is equal to h, is at some specific coset, which is the trivial coset, right? This is positive, right? Let's write here, sorry. This is alpha greater than 0. And so for any h exists t, and there exists alpha, which is also alpha of hx. Okay, some positive number. Right? That's what irreducible means. I can get to the trivial coset in a certain finite number of steps. But what does this mean? hxt equals h. This is classical group theory, fundamental group theory. It's xt is this means xt is in h as an element in the group, right? So this would mean that when I start here, right? So for any, so this would mean if I start in this coset, what does it mean to start in this coset? So now this gives me something else. For any y inside this coset, if I start from y, right? If I start from y, then in the projected chain, I start from the coset, right? If I start from the coset, I can reach at time t, I can reach h. So this means I hit h, and I can do t plus here, right? Because okay, yeah. So if this was a trivial coset, I could do a t plus. Okay, I can always ensure that this t is strictly positive. Right? Just take the next one. Okay.
T is a real number.
Yeah, t is some natural number, some time. Some natural number. I can find some time. You're working on the cosets. It's irreducible. You can, how far can it be? At most n, if n is the index, at most n steps away. Just walk. There's a path to get there. So you walk there. How much does it cost you? It costs you whatever it costs. Just some numbers. They depend on everything here, on the mu, on the g, on the h, just some final numbers. But what this means, if I interpret it back upstairs, then it means that any guy that's in the coset, there is a probability that before time t, I've already come back to h, right? And this probability is at least this alpha. Okay, now alpha and t only depend on the coset. So there are finitely many of them. So I can take minimum on alpha, maximum on t, right? I can take. Okay.
For the starting point.
Write it this way. The probability starting from y that I've hit h, come back to h, up to time t, this is greater or equal than the probability that hy, which is hx, because y is taking the coset of x, right? Greater than the probability then that the coset at time t is the trivial coset. Because if this event happens, this event happens. Okay? And this is alpha. Okay? Do you agree? This event is exactly the event xt is in h.
Yeah, this xt in h.
It's the same event. And if this happens, then of course this happens.
Sure.
Because I took t positive. So that's why I can put the plus in. But just make sure if the first t was 0, then take the next t. You still can do it. Go back and go one step and then come back.
Just forgot. I just missed the xt in h, like I said. But
Okay.
this is exactly th plus.
Yeah. This is not the th plus is equal to t. It's th plus is at most t. Maybe you were there before. Okay. Okay. So we have that. So now we take our specialty. So now I'm still going to use t. There the t's and the alphas were dependent on something. Now I'm going to use the dependent. So I take this to be the maximum over all cosets of t of hx, and I take alpha to be the minimum over all cosets of alpha of hx, right? So then this equation inequality holds with a uniform t and a uniform alpha, right? Because I just made t bigger and alpha smaller. right? So again, what I'm going to write is that for every y g, probability that I start from y, that t plus h is less than or equal to t is at least alpha, some positive number alpha. Now this is uniform. The alpha, the t, and the t are uniform in y. This was very important. Okay, I can get a uniform y. Now you see why is it true? It's true because in the projection I have only finitely many things to deal with. If I had infinitely many things to deal with, I couldn't do this, right? And also, of course, the theorem is wrong. Okay, is everybody with me? What does this mean? How do I get exponential decay from this? Very quickly, right? Very easily, right? Let's start writing. So what is the probability? Right, this is what we want to bound from any starting point x now, okay? Starting where we said for any x, what is the probability that t plus h is greater than t? If we get an exponential tail for t plus, I don't remember what I wrote in the lemma. If we get an exponential tail for t plus, we also get an exponential tail for t, of course, right? Because t is smaller. Okay, this is not the same t. Oh, okay. So I'll do s. Sorry, because I fixed now a special t. Okay, we're going to use the special. So what is this? Well, what do I do? I mean, if s is less than t, this is bounded by 1. But if s is bigger than t, then I start peeling off t steps. Try, fail, try, fail. I have a uniform bound using the starting point. Use the Markov point. So this is equal to, right? The probability, if you didn't succeed in s, then you definitely didn't succeed in s minus t, right? And sorry, you definitely didn't succeed in t steps, right? Okay, now I can condition on this guy. This is good for s bigger than t, okay? For s greater than t. If s is at most t, then I just use, I can bound it by 1. It's just a constant, okay? Now, if s is greater than t, then I can always write this, okay? And now when I condition on this, what happens? So let's write the conditional probability. Okay, this is a conditional probability times, of course, the original probability. So let's already put in the inequality, right? The opposite of this happens with probability at least alpha. So this event happens with probability at most 1 minus alpha. This is where I get my exponential. See, term smaller than 1, I'm going to get many terms like this. Okay. Now, what about this? This I'm going to use strong Markov property, SMP strong Markov property, to say that this is equal to. What is this equal to? I stop at this. Yeah, you have to be careful. I stop at the minimum between t and th plus. So this is strong Markov property at this time. That's a stopping time. Okay. What happens at that time?
At that time, we were at h. No. Yeah. No.
Well, it depends if which one of them is smaller. But
yeah.
I'm just stopping at that time, right? So I have something that's conditional. This is in the. No, sorry. Actually, you're right. I don't need the strong Markov. I just need the Markov. This thing is measurable. This thing is in FT.
Right.
Okay.
We didn't prove it, but this is
because it's a stopping time. Because TH plus is a stopping time. This is in FT. Well, its complement is in FT. The definition of stopping times. So this is in FT. So when I condition on this, what do I see? I see a Markov chain that did something. I don't know what it did. Starts from somewhere. Okay, starts from somewhere, but now has to ask something about time s, but from time t to time s in the future, that's s minus t steps, no longer s steps, right? Because it restarts. So this is some starting distribution. I'm going to say this is at most, whatever is written in the starting distribution, it's at most the supremum over all possible starting distributions. Okay, see why I want a uniform number y, okay? Of what number? I just want to not reach h in s minus t steps. 1 minus alpha is constant, it's outside. Okay? Again, conditioning on what happened here, what do I want to do? I want for the rest of the Markov chain, the rest is S minus T steps, not to hit H. Okay? So this is a superrule, right?
Small, less or equal.
Less than or equal, yes. Okay? Less than or equal.
Do we have to consider like the probability of the condition divided by the probability of being at y? Something like that?
Again, when I condition on a specific event, I have that event. What you can, the way you can think about it is you know, the conditional probability with respect to ft gives me some number, but when I partition it, say on the event and its complement, then I know that that event happens. Yeah, the probability is cancelled. Okay, so I get this, but you see now I can take supremum over x here. This is true for any x. This bound does not depend on x. So I take supremum over x here. Okay, and what I get is that this number, supremum over x of the probability that t plus h is greater than t, right? Greater than s, right? It satisfies an equation, right? Which is this. So let's give it a name. Let's call this psi of s. Okay, psi of s satisfies the following equation. It's always less than or equal to 1. But if s is bigger than t, it's less than or equal to 1 minus alpha times psi of s minus t. So you can go down. I mean, this is standard trick to do. I mean, think of it, you just do it many times. How many times can you do this? Right, so there's a bound on time. You keep going, you go s minus 2t, s minus 3t. How many times can you do this? You can do this kt for k times, so that kt is still say kt is still less than s, right? So you can do this at most.
Wait, t is fixed.
T is fixed. Yes.
Okay.
We could have also written it this way. Yes, really. So you can do this for k such that kt is at most s. So this means that you get the psi of s, which is the number we're trying to bound, is less than or equal to, right? 1 minus alpha to the power of how many times t s over t integer value, right? Because that's for each one of those you get a 1 minus alpha. The last one you get a 1. And this is exponential decay. I mean, I can -1 get a constant. That's fine. Yeah.
Bitwise is not a strong Markov property because you're not using standard.
So what I said is,
time.
I just look at this event is in FT.
Right.
So I give you all the information in FT. That's just the Markov property. Tell you something. I tell you an event that happened. I took an event. This is an event A, right? And I told you I conditioned on an event that's measurable with respect to FT, right? To A. So what does it give me? It gives me, the Markov property tells you, you get some starting distribution, which depends on this event, right? Some average of points that depend on that event, okay? And given, for that starting distribution, you look at the event that's the continuation of the Markov chain for S minus T steps, okay? So that's just the Markov property. And so what this said, so what this actually said, the Markov property, if I wanted an equality here, this would say sum over y, nu of y, where this nu depended on the event A. Okay? This nu depended on the event A and also depended on the starting position here, x. Right. Okay? So this would depend on x, and I couldn't do a supremum over x here if I had this. And also it depends on the specific event A and everything. But what I said is, so this is just a Markov property at time t. But what I said is that if I bound it by the, if I bound this quantity by the supremum, right, then this just sums up to 1. So
right.
I can bound everything by the supremum. No matter which y, I mean, just think of it really intuitively. You condition on something happened at, up to time t. So saying something didn't happen is saying something happened, right? So something happened at time t, the condition on it. This affects where I am at time t. There's some distribution of where I am. But then I say, well, wherever I am, I just bound it by the worst case.
So if S is greater than T, then those two.
If S is greater or equal, if S is equal to T, then this is 0, and this number becomes 1. As long as S is at least T, you always get some. As always S is greater, strictly greater than T, then.
Because I think you can't use this.
Yeah. So I need this. It has to be strictly greater than T to get that. So yeah, so this would not be this, but rather this would be this minus 1.
But also S equals to T, then T plus H. Surely greater than 0.
Yeah, but I don't get the 1 minus half. The 1 minus half already came out from conditioning on this. Maybe maybe I do get the 1 minus half. I do get it from the first one. No, it actually works. It doesn't really matter because I can do it. I can just do a minus 1 here. It's not so important. But if you think about it, it does work. If S is equal to T, I have here bigger than T. That's already a bit smaller than 1 minus half. That's what we had before. Right. Probability that it's at most T is at least 1, at least alpha. The probability is bigger than T is most 1 minus.
Can you repeat again what you wrote and then that instead of we should take a sum of what of the probability of.
Yeah. Okay. As a conditional expectation, what is this equal to? I write the probability X of T H plus bigger than S, conditioned on FT. Random variable, conditional expectation. What is this? This is equal to, this tells you start at XT. Okay, that's what it tells you. Start at XT, that's some random distribution. Okay, start at XT and ask for the probability that TH plus is bigger than S minus T, right? You need to go for another S minus T steps. Okay, because one event is contained. And yeah, you have to be careful. Sorry. Yeah, okay. No, so this is not completely good because I started, it is true that I started XT, but here I'm asking to never reach S. What if I reach S? What if I reach before T? So, this would be,
no, because the condition of the event, not on other.
So this would be starting at XT, but the distribution of XT would be conditional on the fact that XT never reached.
Yeah. Because we condition on the event.
Yeah, so the way to write it would actually be yeah, so maybe not conditional.
Yeah.
What do we say about the Markov property? If I put here an event A, which is measurable with respect to FT, any event A, we said that this is equal to the probability X of A, right? Times, if this is measurable with respect to FT, I need this event to be to start from some starting distribution, right? That A tells me what the starting distribution is.
Condition on A.
So yeah, so what I can do is sum over Y, probability that XT is equal to Y conditioned on A. Okay, and then I get the probability starting from Y of this thing, right? I mean, this is technical. It's just
no, but
okay, no. As soon as I bound this by the supermove, then I get. Okay, so let's take a break and.
לא, בעיה שאפשר לנסח כאילו למישהו מהרחוב, כאילו זה מה שאני יפה.
כן, אני זוכר שראיתי את זה, הייתי בתיכון, ראיתי את הכותרת, לא ידעתי כלום על מתמטיקה אז, אמרתי, טוב, אני מוכיח. אם זה בטוח נכון, אני עכשיו להוכיח את זה. חשבתי איזה חצי יום לנסות להבין לא כל כך קשה.
והגעת לעקומות אליפטיות
לא הגעתי
אתה יכול לעשות
אפילו,
רידוקציה
לא ידעתי שום דבר, מה, אני
לא, יש כל מיני
הייתי קודם כל ב3 יחידות, לא
באמת?
לא ידעתי מה לעשות. זה לא, סתם הייתי.
אתה מוכן לתת עכשיו שיחת תה על מ3 יחידות לראש המערכת?
ההיגיון שלי אמר שבעיה כל כך פשוט לנסח אותה, לא יכול להיות שכל כך קשה להוכיח אותה. זו פעם ראשונה שנחשפתי למשהו, שאי אפשר, שההוכחה היא מסובכת לאין ארוך מהרקע שצריך בשביל להבין מה באמת הבעיה.
יש גם את הבעיה הזאת עם השלוש אין ועוד אחת או משהו, נכון?
קולץ.
זה גם אתה יכול להסביר
אומרים לא להיכנס.
קולץ יותר איתה הוא עשה משהו.
הוא התקדם שם?
כן. אני בדיוק התחלתי לחשוב על זה. התחלתי לחשוב על זה, היה איזה רעיונות לעשות קולץ מקרי, ואז תראי הוא עשה קולץ מקרי. איזה כמה שבועות שחשבתי זה קצת, לא ממש.
הוא קצת פריק של הטבע, לא? הוא לא בן אדם רגיל.
Okay. Okay, so a reminder. For random variable, so to say that something has an exponential tail, I'm going to write it with a t. This happens if and only if. So this means exists delta for every little t, right? This happens if and only if exist delta and c such as for every t. This is if and only if the expectation of e to the epsilon t is finite, and here it exists some epsilon. Okay, and you can try to understand the relationship. Why am I saying reminder? Well, it's not a difficult exercise, okay? If you have this, then you can prove this by just somehow understanding what goes on here. And if you have this one, you can use Markov's inequality to get the exponential term. Okay? Because the probability that this is bigger than t is this is the same as e to the epsilon big T bigger than e to the epsilon little t, and then you can use Markov. So the translation from delta to epsilon back from epsilon to delta might not give you the same delta. Okay, so you might lose some things when you go in between the two things, but they're equivalent as statements. I'm going to use that fact. And first, the proposition I want to prove. First proposition, a definition. Definition. U is a random walk group, and H is a finite index subgroup. I want to define a new probability measure on H. This is what I want to define. Okay, so I want to define a random walk on H, which has to do something with the original random walk that I started with on G. And this random walk is going to be, if you think about it, just, well, what can you say? We know that the random walk is going to repeat coming back to H. Why? Because the return time has an exponential tail, so it's always going to come back, right? In fact, quite quickly, it's going to come back on average.
Okay. You can the previous exercise, lemma the G infinity? Did you use the infinity part?
No. It was true in more generality than that, but I don't want to. I didn't use. I only use it. It's basically a finite function. What I want to. Okay. So what I want to do, I want to define a random walk on G. The way I'm going to define it is by looking at the return times to H. This is a sequence on H, okay? And I claim that this will be a random walk on the group H, in the sense that it will be a product of elements that have the same distribution. Going out of H and coming back to H will give you the same distribution, even if you kind of start from a certain element in H and wait till you come back to H. Maybe in one step, right? Maybe the next is also still in H. But the difference between them in sense of group, right? The element you need to multiply for the difference between them will exactly have the same distribution. Okay, so we're going to define the measure. So define mu sub h, okay, of x. This is for x in h. Okay, so this is a probability measure. X in h, mu sub h of x is the probability that you start from the origin. Remember, this is starting from the identity, and that at time th plus, which is almost surely finite, so I can write this, I'm at x. I hit h, I return to h at the point x. I started in h and I return to h at the point x. Okay, so this is a probability measurement. And this is, we call this the hitting measure. So this defines a random walk on H. I mean, if you have a probability measure, you have a random walk, right? But what does it look like? So let's do a few things. First of all, proposition. If mu is in SA G infinity, then UH is in SAH infinity. Okay, so symmetric is easy, right? Symmetric is easy because it just follows from the symmetry of mu. Xt and xt minus 1 have the same distribution. Okay, any path that gets to x, the minus 1 of it will be a path that gets back to x minus 1. So basically all we need to show, so I'm only going to prove the exponential tail. Okay, you keep the exponential tail. Now, typically, this is the point why I like to use these exponential tails, because exponential tail will be preserved by moving to the hitting measure, but we'll see in a second that finite support, for example, will not be preserved typically. So the right world to look at is the measures which have exponential tails, not necessarily finite support. Okay? This is the main reason. So the proof, how do we show exponential tail? Well, so there exists C and delta, right? Such that for every t, the probability that th plus is bigger than t is less than or equal to ce to the minus delta t. This is what we just proved, the exponential tails of the hitting the return time. This follows from the finite index. Okay? I've only defined hitting measures for finite index. Okay, it's possible to define for other things. I would need to prove some things when it's well defined, but at the moment it's only well defined if I know that this is, I'm guaranteed that this is finite, and I'm only guaranteed in our stage of understanding, we're only guaranteed that this is finite if we have a finite index of it. So don't be confused. It's not, you can't define it for any subgroup. Okay? Yeah.
How is it well defined? If they start at one point in H or other point in H,
this is starting at 1. When I don't put anything here, it means I started at 1. It's just some number.
Okay.
So define the probability measure. You're asking why would it be the same thing as what I described earlier? We have to prove that. So that's a different thing. Okay. So this is, so the probability that th plus is bigger than t is less than this. So this we know. So now notice that when I look at the exponential of e to the epsilon, let me write 2 epsilon th plus, right? Is this what I wanted to do? So it's 6 plus. when I look at the expectation of e to the 2 epsilon x1 in absolute value. Now remember,
Epsilon is from the reminder.
what?
Epsilon is from the.
No, epsilon is not from the reminder now. It's just some epsilon. Remember that I know that there exists an epsilon from which this is finite, right? There exists an epsilon for which this is finite because of mu is in SA infinity. That's what it means, right? So at some point this is finite, and when epsilon goes to 0, right? Where does this converge to? So by dominated converge, I mean this is dominated by the first epsilon for which this is finite, and by dominated convergence it converges to 1, right? E to the 0 is 1. Okay. So this thing converges to 1, so I can make it as taking epsilon small enough, I can make it as close to 1 as I want. Okay. So I'm going to choose, and I put a 2 here on purpose. I'm going to choose epsilon such that this expectation, see, this comes from the SA infinity of mu. So this expectation is less than or equal to e to the delta, where this is this delta. This is a number bigger than 1. So I can make this smaller than this. Okay. Why did I do that? So now I have to check, right? How do I prove that I want to show that for this epsilon, the e to the epsilon of one jump of one jump of the mu h walk, right, will be finite. Okay, so I need to bound the expectation. What is one jump of the h walk? It's just starting from the origin. It's just e to the epsilon of xth plus. Right? Don't need to worry about which absolute value I'm using, right? Because they're all equivalent, right? If you show it for one absolute value, you showed it for all. Okay. So I need to show that this is finite. So I need to bound this. So how do you bound this one? Write this down. Sum t goes from 1 to infinity of probability of sorry, not probability, but rather expectation of indicator th plus is t e to the epsilon t xt.
What is this? What is this? If it represents?
This is equal to sum over all
No,
x
the
mu hx e to the epsilon x. That's the exponential moment I need to bound to show that mu h is in SAH infinity.
Oh,
Okay. I just wrote it in a probabilistic. Okay. This is starting at 1. I'm not claiming anything about all the return times means. I want to just showing this one step of this measure has an exponential moment. Okay. So this thing, how do I bound this expectation? Well, in this case, it's easy. If I were to do with if I didn't use a mu SA infinity, it would be harder. Okay? I would have to be careful. Well, it's everything is non-negative, so. So this is less than or equal to the sum. Each one of these expectations, I just do a Cauchy-Schwarz, the product, right? So it's the expectation of this squared, the expectation of this squared, and square root on everything. Okay? So square root on everything. This is Cauchy-Schwarz, right? What is the expectation of an indicator squared? Indicator squared is an indicator. Expectation of an indicator is probability, right? So I get probability th plus is equal to t. Okay? And then here, what do I get? Here I get expectation of the square of this thing.
Why is the K?
I don't know. There's no t.
What?
Now, okay, what do I do with these guys? Right, so this guy I know how to bound. This is just exponentially small. I don't care about the square root, right? Just something exponential in t. All I need is this will sum up to something finite. So this decays exponentially in t. And this thing, what is it? What does it look like? Well, xt is u1, ut, where these guys are independent, right? These guys are independent elements, u elements. And so the distance by triangle inequality is most the sum of the distances. Okay, so this means that this thing is less than or equal to, everything is non-negative, so I can use the, so this is less than or equal to what? E to the 2 epsilon sum j equals 1 to t uj, right?
Yes.
But these are independent, so expectation of, okay, exponential of a sum is a product. Exponential expectation of a product of independent things is the product of the expectations.
You know, these are independent because the exponent is a continuous function, right?
No, they're just, I know that they're independent. They are independent random variables.
Yes, but you get new random variables, which is the e to the power.
Yeah, e to the sum, this is the product of the e's. Do you agree?
Right. As I'm saying, these are independent now.
These guys are independent.
This is like something we haven't.
Functions of independent are independent.
This is not what I'm asking for.
We didn't see it for like a general group and we saw the metric and the.
What didn't we see?
I don't know. Sorry. Yes, that's it. Okay, never mind.
These
Yeah,
just
no,
real valued functions of independent random things.
No, I
They're
talked
also
about the-
independent random
I
variables.
talked about the norm of xt is the sum of the norm of.
It's bounded by the sum.
Yeah, it's bounded.
So a triangle inequality.
Yeah.
Okay, so you have to remember what the norm is. The norm is the distance to the origin, so you can bound it by the sum of the distances to the origin. Right? So what we get is that we get the product of the expectation. Now, when I put expectation on one of these, the u's, what are they? They just have distribution mu, right? So all the u's have the same distribution as u1 or x1,
Excellent.
right? Same distribution all of them. So what I get here is at the end of the day, this is bounded by, okay, let's put in everything. Sum t equals 1 to infinity. I have k, I don't remember if I used k or c. So c e to the minus delta t, right? This is for the thing. I have the square root, right? And then I have expectation of e to the 2 epsilon x1, okay? E to the 2 epsilon x1,
The power.
all of this to the power of t, right? Because I have t of them. Now, what was this? This one was less than e to the delta. I should have done delta over 2.
Yes.
Okay, so
Delta over.
assume that I did delta over 2. I should have done delta over 2. Wonder why it's no, of course not. I should no, I don't need to do delta over 2. There's square root. There's square root here. But then it's over
So
here. What? I mean, it's not a problem, but when did I write? Okay. In my notes, I wrote that this decays like 2 delta. I did 2 epsilon and 2 delta. Okay, so pretend that the delta was chosen, so this is 2 delta, and then this was chosen less than e to the delta, so I have 2 delta plus delta. I get e to the minus delta, and so everything is less than or equal to the sum of c square root c times e to the minus 1 delta, and then I have a square root to delta of 2, but this is finite inequalities. So you see why it's very easy when you have exponential. If I was trying to preserve it, it's true that if you start with a kth moment mu, and you move to the hitting measure, you get k moments as well. Okay, which is the best you can hope for. So, but that proof is much more complicated. So, yes.
Just the inequality of How did you bound the probability? By what we've shown, that it over there is the probability of equals to t, and over there is like the
Well, equals is less than or equal. Greater or equal. So, yeah. To be a t is even more restricted. Okay. Maybe I made a mistake in some of the details. You can definitely fill it. It's another 2 or greater or equal might be the same.
gotta follow the very detail.
Well, I mean, I might have. There might be some typos. There might be some typos, but it's not gaps in the proof. It's just you have to choose a delta and epsilon. Okay. Theorem, the main theorem I want to prove. Theorem. Exercise. So again, we have this situation. Xt is a mu random walk for mu inside SAG infinity. Prove that. Oh, I didn't define something. Okay. T0 is 0. T k plus 1 is going to be the smallest t bigger than tk, such that xt is in H. So these are the successive return times to H. Successive return times, okay? So just define these. So T1 is exactly the return time to H. T2 is the next return time to H, and so on and so forth. And prove that Y n, which is defined to be xtn, so the nth return time to H, prove that this process in n is a UH random walk. Okay. This includes proving that everything is well defined. For example, that all the TNs are finite on the short. That's easy. It's just a strong Markov problem. Proving that this is exactly a UH random. Okay. Meaning that you can write Y as a product of UH independent random variables. So this is what I said. So if you start with a random walk on a group and you only look at it at the times where it's hitting a finite index subgroup, then you see a random walk on the subgroup and you know exactly the measure which governs, which is the hitting measure. Okay. This is a very useful tool to be able to pass the finite index subgroup. And the theorem I want to show is that if I have finite index then remember harmonic functions of polynomial growth of degree k are isomorphic to the same thing H, but here with the heating.
One place we use the finite index was say there are finitely many cosets, so we can take the maximum and right.
So it gives us exponential tails. It gives us that the time is almost short infinite. That you can even define the hitting.
It's more than just take the maximum. I mean, if we knew that somehow those t's
For example, if the index was
uniformly bounded,
if the index was z, so if you have a quotient which even a normal subgroup, the quotient is z, then the hitting measure will be well defined because the return time will be, because z is recurrent, the return time will be almost short defined. But it is no longer true that this return time has exponential tails. In fact, it's going to have infinite expectation. We already showed that the time to get to a point even adjacent is infinite in expectation. So as soon as you breach the finite index, you don't, it's a completely different game.
So what we've shown so far is that you can define everything, and we've defined that what was the purpose of the exponential thing?
to say that we kind of live in the same world. This new space is in the same category, if you want, as this space. Exponential tail measures on it. So if I had a finite orbit thing, it would not be the same category. I could still write this, but the correct category that you preserve the properties is exponential moment. Okay, so proof. I'm going to prove that these two spaces are the same. Isomorphic. This is as what? As linear spaces, as vector spaces. Okay, that's the isomorphism. So I'm going to tell you what the linear map is. The linear map. So the isomorphism is linear isomorphism. Is just restriction. Restriction is a linear map, right? Take a function restricted to subset. It's a linear map. So what do you need to show? You need to show this linear map is surjective and that the kernel is 0, right?
Like a restriction and an induction in some sense, like what the inverse.
No, I don't want an inverse. All I need to show is that I get every function in the image, right? So in these spaces, from here I can get any function here by restricting. That's surjectivity, right? And then I need to show that the kernel is 0 for injectivity. So what do you want to do first? Surjectivity. Okay, so how do we get? So how do we show that? Okay, so step 1 is we show that it's surjective. Surjective from specific spaces, right? I mean, of course, restriction is surjective, but okay. So what we need, so start. So you take any function in this space, in the image, right? And you need to find the function such that it's in the original space, right, upstairs, but its restriction is exactly f tilde, right? That's what you need to find. Any suggestions?
Can you repeat?
I took a function in the target space, and I need to find, so we want to find some f, which is a function on G, but not just a function on G. It's a harmonic function of polynomial growth at most k, and harmonic with respect to u, right? Such that, we want to find such that the restriction to h is exactly f tilde. That's what we want to find. F tilde is a function defined only on h. Okay? That shows that it's surjective, right? So what do you mean?
No, I think about it has a lot of meaning, but maybe with the coset or something like
Because of a finite index, they extend it using the fact that it's harmonic.
push
How do I
forward.
extend it? Right?
You know what is harmonic on H?
Harmonic with fixed on it. Any guesses? What would happen if f would be harmonic? At the end of the day, it's going to be harmonic. What would happen? Yeah. If I find such an f,
It would be a martingale.
yes. So what would happen if it's not again? What?
For x2 would be.
Yes.
So that defines the
So what could I say
Also,
exactly?
F of y t would be.
So what could I say about f of x? Suppose I found such an f. What would f of x be?
It's the integral of
Yeah,
the
so it's
expectation
starting from
f
of
I have of this function.
F of xt.
this would be true if it was a multi-val, right? But also I could put here stopping times. Do you agree?
Yes, because of the optional stopping. No? Yes.
Right? I can do this,
I'm just talking about it.
right? Well, if it's uniformly integrable, I can do this, right?
Do we assume?
Okay. Well, suppose I found something, right? Yeah, this has exponential tail and this grows polynomials. So okay. But then if now I know I'm in H at this point, and
So you can
I'm assuming I found it, right? So I can put the restriction. But this gives me a definition of what f has to be. So if I can solve this problem, there's only one way to solve it. Okay. So we define this. And now we prove it has the right properties. Okay. Now, first of all, if I define this, I need to show it's well defined. I need to show what you said is that this,
Does not depend where you land in H.
yeah. So, well, it's well defined because this is almost surely finite, right? Okay, so it's almost surely finite, and we also want to show that that this is yeah, okay. So it's well defined, right? I mean, I just define the number for every x. That's all, right? Because this is an almost surely finite stopping time, so I can define this number. Oh, I need sorry. The fact that it's almost surely does not mean that this is integrable. I need to show it's integrable. That this function is integrable.
defined, like,
right?
The fact that it's almost surely finite.
I need to show this expectation exists. This is not a non-negative function or something. It could be infinite. I need to show an expectation exists. So first of all, why does this exist? Because expectation x f tilde x th plus, right? Let's even put absolute values. This just makes it bigger, right? So I need to show that this is finite. Well, this is less than or equal. So f tilde comes from hfk. Remember what hfk is? There is some c of f tilde, right? Such that this is less than the distance of this to the origin, right? Okay. So this is less than or equal to what do I want? C f tilde expectation of x th plus 1, all of this to the k. Okay?
Yes.
So now I need to show that that's finite. But this is easy. This has an exponential tail. And this guy cannot move basically more than the number of steps, maximal number of steps it has. Right? So, okay, so I'm leaving this as an exercise. It's not a difficult exercise. You could do Cauchy-Schwarz, or you could do okay, I'll do one more step. This is equal to Cf tilde sum over t goes from say 1 to infinity because of this expectation of x 1 th plus is t, right? And then I here have an xt plus 1 thing. So everything is in the expectation xt plus 1 to the power k. Now you can see that you can okay, you can't use a Cauchy-Schwarz because you can't do a 2k. We only know that that this has a finite kth moment, but you can play around with this and show why this will be finite. Okay.
Don't we know that they're nested? I mean, if it has finite kth moment, it does no, or is it nested to the other direction? I mean, if you have finite kth moment, you have finite k minus 1, but not
yeah. Or, I mean, that's one way of doing it. Another way would just be to say that I can add another constant here. This constant depends on mu and on the specific choice of whatever the absolute value is. Okay? Where this thing, what is it? This is a product of th independent guys, right? So it's less than or equal to c mu of the expectation under x of just of th plus 1, all of this to the power k. And the fact that this has an exponential moment tells you that it has all moments.
Why is it?
So you need to show that xt is always less than or equal to some c mu times t. Wait. That's maybe not true. No, that's only true if you have a finite support. Sorry. Okay, I'm going to leave this as an exercise. Yeah, what I wrote here is only true if you have finite support. Again, mu has exponential tails, and so does this guy. So this gives you an ability to bound this by some finite number. Okay. You have to be careful with the kth moment on the x's. The kth moment. Sorry. No, you don't have to be worried about the kth moment on the x's. Yeah, what I said was on. Take what I wrote before. No Cauchy-Schwarz. the distance xt to the k is finite because mu is exponential tail. I'm not using, I'm thinking of a different. So as mu is exponential tail, x to the power k, xt to the power k will be finite.
For
Okay.
every K?
What?
For every K.
For every k.
That's the assumption, right? That,
Yeah, well,
No, the
exponential moment
assumption
is stronger
is
than finite moments. Yeah. So you just split this using a Cauchy-Schwarz. So you can get, instead of k, you can get 2k.
That's finite.
That's still fine. It's similar to what we just did before with the. You have to split somehow the random time into a deterministic time using Cauchy-Schwarz. Okay. We did to the other direction.
And Ariel, the fact that it's harmonic is fair. I mean, we constructed it.
I want to prove it. I didn't finish the proof. That's what I'm saying.
Okay. I think that's missing is, you know, that if you have the
It's not trivial. Let me do a few more minutes. I want to prove that it's harmonic. Okay. Let me just go prove that it's harmonic. I mean, I have to prove that this function is a. Yeah. So I'll leave it as an exercise also to prove that this function is bounded by something, some kth power of the distance of x. Okay, that's not difficult. But what I want to prove, so this also needs to be shown basically, or some c, which depends on f. Okay, you just use the definition to prove that. But I mean, you could basically, together with that, you can actually get the correct bounds. But the thing is to show that it's harmonic. And what I want to tell you, what I want to prove is that f of x is also equal to this. Not just plus, but also the original. Okay, why is this true? Let's check case by case basis. Okay, if x is not in H, then TH and TH plus are the same thing. Okay, now if x is in H, then I need to somehow show that this is the same as writing a TH plus. Okay, so how do I do that? So I start with this. Now I'm assuming that x is in H. Okay, and I want to somehow get f of x. But then what you notice is that this guy is harmonic, right? So this is equal to, starting at x in H, f tilde of what? Of the first time according to mu H tilde. Okay, so maybe I write it differently. I mean, this is sum over y, right? Mu of mu H of y of f tilde at xy. That's what it is. Right? Because you start at x and you take one step according to, right? Because TH plus is one step according to mu H. Okay? But then we assume that we started with a harmonic function. So this just becomes f tilde of x, which is f of x in this case when you start with x in H. So this proves that you can always put a non-tilde, a non thing here. Okay. If x is not in H, then they are actually the same thing.
Yeah.
And if x is in H, then TH is 0. So this is f of x, f tilde of x. And that's what I showed. Okay, because of the harmonicity of f. And now using this, you say that that f is also harmonic on G. Okay, because now you look, f of x is equal to expectation f tilde x th plus. Okay, now th plus is at least of time 1, so I can take this expectation and condition it on x1, right? And take a further expectation. Okay, And what I get here is the following. So how do I compute this? So when I condition on the first step, TH now becomes, TH plus becomes TH. It's the first time I'm in H from this time, not from time one, right? That's just a Markov problem. So what I get here is I get this. So, and then what is the expectation over x1? It's just summing over the possibilities, right? And it's under this, it's under starting from x. So you go over all y, you have to go from x to y, right? Once to go from x to y, this is
UY.
I can do mu y,
Or UY.
and then the point will be xy, right? That's what x1 will be. And then I need the new expectation of this, but th started from x1, which is xy. So this expectation starting from xy of f tilde of xth. This is the correct way to write that as conditional. But this, I just proved to you, is the same as f of xy in any case. If this is an h, if this is not an h, both of them give me just f of xy.
Can you repeat this?
So what I get here is just the sum over y, mu of y, f of xy. This equality is harmonious.
Can you repeat the first equality?
This equality?
Yes.
Again, when I condition on x1, what is the conditional expectation? So the conditional expectation inside is you start from x1 and go to f tilde of x, in this case th, not th plus. It's th plus. If you condition on time one, it becomes th because it only started looking after time one, but now it looks from now. Now it looks from time zero when you shift time by one. Okay.
Started at x and you moved one step, and now you're at xy for someone.
Yeah, I wrote this like this. This is expectation under x1. There's another expectation on this expectation. This is a random variable. Expectation under x1 of f tilde of xth. So you start from this random x1 and you ask what is the value at the first time I'm in h? Because this was the first time after time one, meaning that when you start from x1, it's the first time.
And now you're assuming that.
And now I'm saying, what is the expectation of this random variable? It's the randomness is here. So I just go over all the possibilities of this thing. What are the possibilities? The possibilities are xy, where y is generated by.
But do we do different between this part and the second part?
Which part?
On the first part, we show that xt f of x is like we can.
I wanted to say what this is. I needed to know what this is.
Okay.
It doesn't say a plus.
Okay.
If it had a plus, I would be fine, but it doesn't say a plus. So I need to understand that if I don't have a plus, this is equal to this. I still have the second half to do. I was hoping to get that right. So the injectivity. Injectivity is basically an optional subject. Anybody remembers that?
So,